So good morning. I'll talk about, as the slides say, making free data universally accessible and useful. And of course, it should be clear to everyone where this comes from. Thank you, Google. The setting of this talk is this. If we're going to have computers, autonomous agents, robots that operate in the world successfully, they have to have deep knowledge of that world. And even more, if we want to have agents that collaborate with us in doing various tasks, they have to understand the world the same way that we do. And this brings me to the central theme of this talk, which is to focus on machine learning that is, one, object-centric, and two, 3D-based. Clearly, the world is complicated, but it is decomposable. There are these stable entities we call objects, things like furniture, objects, cars, aeroplanes, people, animals, and the world can have many arrangements of these entities, but their properties go along with them. So it's useful to think about them as units. And as Fei mentioned, there's been tremendous progress in the last 5 to 6 years using deep learning methods in understanding objects and images, being able to detect them and understand their category. And this has been due to many things, but in part due to the availability of data coming from images, for example, and also lots of computing power. However, this business of just categorizing objects and images is not sufficient, in part because the number of categories keeps growing, which means we need more and more training data, but more fundamentally because categories is not knowledge. Categories connect to each other, and what we need is to map sensor data to some global understanding of what's going on. And understanding the ontology of the world is very complicated. So to simplify things in this talk, I'll take a specific point of view that goes back to a really old idea in computer science, something that was a big topic 30 years ago, being object-oriented. What that meant back then is that, say, if you look at an operation like plus, it can be complicated because it has to be polymorphic. It has to be able to add integers, rationals, floats. But if you specialize it to a specific number type, if you associate plus with a number like 3 as an integer, then plus can be simpler because it only has to know how to add integers. And the same intuition here. If we focus knowledge on specific objects, then the structure of knowledge can become simpler because that single entity kind of unifies all that we need to know about it. And given that the world is 3D, the approach that we'll take in this talk is to focus on 3D representations of objects, put them at the center, because after all, of all the digital forms we have of information about the physical world, 3D is the closest to the actual physical artifact. And so the idea is I want to somehow pull knowledge on top of 3D. Given this, say, 3D model of the Arc de Triomphe in Paris, I'm going to take all images, all videos, all web pages, all novels that talk about it and aggregate all this knowledge on top of the 3D. This is a new use of 3D. And 3D has been used to create nice imagery, has been used for gaming, for physical simulations, but I want to do knowledge aggregation on top of 3D. And this brings us to one effort we have in my group, ShapeNet, where the idea is to collect lots and lots of 3D data. That's becoming much more possible now with low-end scanners. And not just the geometry, but a lot of knowledge and annotations about this data to have information about symmetries and parts and physical properties like weight and size, and also more and more function. Objects have the form they have because they're supposed to support specific functions. And so this is the sort of the big picture. From data, I want to pull knowledge, store it on top of 3D representations, and then transfer the same information to new settings to get value. This transfer process is itself quite interesting from the point of view of algorithms and representations. Fundamentally, a similarity between two objects can be thought of as an information channel that allows you to transfer some knowledge about object A to some knowledge about object B. So in my work, we focus a lot on networking objects, whether they're kind of 3D models, images, and so on, so that we can transfer information between them. And so this is sort of the picture I want you to have in mind of 3D at the center, connected to everything, connected to text, connected to images, to videos, to VR, and so on. And once you have this, once you can pull knowledge onto the 3D, then you can go to a new situation and provide information. Information that is not directly present in the signal, but can be inferred from this knowledge base that you have in the cloud. So let me give you some small examples of this effort. One is to annotate, say, your 3D models with part information. And again, this is part of the ShapeNet effort. And this it's a combination of human annotation and algorithmic propagation. So we ask people to paint different shape parts on views of objects. Then we use a variety of algorithms to propagate this information to other shapes. And this addresses a bit the problem that Chris raised of how to get data. And then we have humans verify the algorithmic annotations, because verification can be done in a way that is much, much faster than the original annotation. Here are some examples of parts generated this way. Now, a key part of this effort is linking different modalities together. I will briefly talk about linking 2D and 3D. Linking 2D and 3D, because they are quite different. And we do so by somehow trying to embed both into a common embedding space, so that images and 3D models live jointly in a common space. And we do so by first constructing the embedding space using the 3D alone, because 3D is a more pure representation of the underlying object. Unlike an image, you see all of the object, and unlike an image, you don't have background and clutter. And then we train deep nets that embed images into that space learned from the 3D. And that itself is interesting, because we construct synthetic images. Because we have 3D, we can create training data. We can take objects from ShapeNet, render them with a variety of lighting conditions, put various backgrounds, put occlusions, and we can generate from a single object millions of training images that then can be used to train a deep net to ignore all the nuisance factors other than the pure object geometry, which is what we are after. And I think it's a very interesting paradigm of trying to do machine learning using synthetic data, but I will not say more about that right now. So once we have this joint embedding space where images and objects live together, we can do all kinds of interesting things. For example, given images, we can try to retrieve 3D models of similar shapes. Or the other way, given 3D models, we can get images of such shapes. Or we can go from images to images in a way that is viewpoint agnostic, because it's all linked via the underlying geometry. And even we can start connecting text with 3D models, which is well done now in the case of images, because we have so much training data from web pages, but there's not very much text linking in a 3D and text. So here's an example that if you query the 3D warehouse with, say, chairs with round backs, you get very bad results, as you can see. I mean, there are some chairs with round backs, but also there's a lot of garbage. But if instead you query Google for chairs with round backs, you get very good images. And then from the images, using the common embedding space, you can go and get very good 3D models. Or the other way, you can now start pulling information from images onto 3D. For example, many 3D models are not textured, but because we have this way to link to the 3D, we can start pulling information from one image to many models. And this means now that we have many more textured models to create better images for training machine learning algorithms. The last topic I want to talk about is using deep nets that directly operate on 3D geometry. And of course, here the issue of representation comes up. There is many for 3D. There is meshes, point clouds, voxel grids, distance fields, and most excellent work for doing deep learning on 3D has focused on either volumetric representations or view-based representations. Why? Because traditional convolutional architectures require a regular structure to operate on, because they do optimizations like weight sharing that requires the same structure here as there. But these voxelized or pixelized representations are not the best for 3D, because if you think about it, voxels can be expensive. Either you have something very coarse, or you have something where most voxels will be empty. And in the view representation, you don't see the inside of the object. So we started to think about how can we do machine learning directly on point clouds or meshes, things that are much less regular than images, for example. And this is sort of a topic that I think is central, how to link better big data in 3D form and machine learning. Let me say a little bit about point-based representations. There'll be a poster this afternoon about that. Again, the idea is now data will come in as point clouds, 3D point clouds. We're going to build a deep net that directly generates from the point cloud classification, segmentation, and so on. And here's, very briefly, the architecture we use. If you look in the top part, there are sort of two stages. So one stage operates purely on the point cloud at every point independently, taking the original XYZ coordinates and generating many, many more functions of those coordinates, like 1,000. Then there is a symmetrizing step where you aggregate all this information in a symmetric way so that the ordering of the points has no impact. And we found that max pooling is what works best. And from that, we generate a descriptor that can be used, for example, for classification, or we can augment the local information with this global descriptor to do things like estimate per point functions, like segmentations. And this is what you can do with this. You can take a scan and classify it. You can take a point cloud and partition it into segments, or you can go into a scene and do semantic segmentation. And here's some more examples of the results. And this is semantic scene segmentation. So it captures the different object classes, as you can see. And what's interesting about this PointNet architecture is that it's very, very lightweight, both in terms of memory footprint and processing. And I think that as we get more 3D into portable devices, this can be interesting for doing processing directly on smartphones. In addition to point clouds, another interesting thing about this method, and I show here, let me skip this slide because I'm running out of time. In the afternoon, there will be also a poster about doing deep nets on graph-based representations and meshes. I don't have time for that here because it's mathematically a bit more involved. But let me finish by talking about going in the other direction, namely generating 3D, having deep nets that now generate 3D in point cloud format. So here you take an image, and you take an object in the image, and then generate a 3D model in this point cloud format. And again, here we are lucky because we have shape nets, so we can generate many training data. We can go from views of models to point clouds of models. And there's many interesting issues in this approach, but I'm running out of time, so I'm going to go a little bit fast over it. One is the loss function, because you have to compare point clouds, so you need something which is end-to-end differentiable. And the other is that since the input is an image, the first part of the network is a standard convolutional network. But the second part, the predictor, the thing that generates the point cloud, actually has an interesting structure. Because shapes have both kind of smooth, normal parts and then little detail parts. And we use two different mechanisms to capture those two. So there's a deconv branch that does a standard convolution to generate the smooth parts, and then a fully connected branch that produces the more detailed parts. And again, due to lack of time, let me skip over the details of this, but I show some examples here where the blue generates what's coming from the deconv branch, this smooth, normal part of the shape, and then the red part comes from the fully connected branch that gives you the more detailed, fine aspects of the shape. And here's some examples where I take an image, I show the same view, and then a different view of the 3D geometry constructed this way. And even the method has been trained in a class-agnostic way across all classes, and is able to be applied to new categories. I think I'm essentially out of time. So the very last thing that I just mentioned is that we're interested in capturing, as I mentioned, physical interactions between humans and objects, and capturing that in some detail. I mean, capturing the dynamics and the physics of the interaction, and ultimately using this to digitize human physical skills. So so that they can be transported both to robots and to other humans. And I'll just say 2 points about that. One is that one interesting aspect is that unlike just understanding objects in images, you have to understand the state of objects. That is the door open or closed? Is the chair empty or occupied? Is the mug empty or full? And then how to represent exactly, these interactions in mathematical ways is also quite interesting, but I'm going to have to pass on that because I'm out of time. So let me finish by saying that the main line of thinking in this research is that if we're going to make 3D data universally accessible and useful, we have to understand the semantics of the data. And the basic thesis here is that the semantics of this data is encoded in all the web of the relationships of data in many forms, in images, videos, text, and so on. So the key goal here is to capture that and to develop new machine learning techniques appropriate for 3D and appropriate for capturing the functionality of objects, the topic that is very dear to my heart now, but I didn't have time to go into it in this talk. So I want to finish by thanking my many students, postdocs, and collaborators, and also the funding agencies that provided support for this. And I'm going to stop here.
Thank you very much. Any questions for Leo? Great. Please join me in thanking Leo once again. Thank you, Leo.